Okay, good afternoon and thank you for joining. So let me just, as promised, go back to integration by parts and review it very quickly and then start a new method. This is what we learned before, but the only difference is that I am just adapting myself with the notation in the book. So we are using U and V in my derivation first. I did it with F and G. And for some reason it was not recorded, so I did it with my iPad at home and uploaded that again. So this is the formula we got. Do you remember what was the problem here? The motivation behind that was that is there any formula for the integral of the product of two functions? We didn't get the formula directly, but we write a formula like this, in which the structure you see here as your integrand is a function with the derivative of another function. And I told you you can view it in this way. You can flip the prime over from V to U, but there are prices to pay. One price is actually to put a negative sign, another price is to put this product UX. And I told you that, of course, in Sweden it's a little bit different. So we actually derived that formula for you as well. So because for this one to work, I need a derivative here. But usually what we have is actually we have an expression like ux just vx, the product of two functions. Okay? And then if I want to use this formula to say something about this, I need this prime here. But the prime is not there. I cannot just put it there. I have to do it in a legal way. So what was the legal way? Do you remember? I copy and paste the first one. But because I need a prime, I remember the notion of primitive function, which I denote by capital V, and I put prime here now. Yes, and then dx. So what is V? V is, this capital V is a primitive function, a primitive for little v, as usual. Okay? But now you can momentarily forget about this, and then you have the same structure you need. Yes? You have a function with a derivative of another function involved, so that I can use this formula. Yes? So if I use this formula, then it becomes ux. So let me write it here for you. So it becomes ux, but v of x without the prime sign. But v without prime sign is not little v, it's capital V. Yes? And then I have minus integral of u prime x, and then v is my capital. So what I did, this is what I want to answer, but if in order to use the formula I need a prime there. I didn't have that prime, so I did it like this. I wrote it capital V, a primitive for little f, for little v, and then put a prime there. Then you can immediately compare this one with this one. U is the same U, but here capital V is playing the role of this little v. So I rewrite this formula, but wherever I see little v, I switch it to capital V. That's the formula. So this is a good one, yes, because this is the integral of the product of two functions. I have a formula for it. But you need to remember, you have to write the first one multiplied not by the second one, as it appears here. You have to multiply it by a primitive of the second one minus the integral of u prime x times capital Vx. So this is the way that in Sweden it's very practical and it's more understandable somehow, because the motivation is clear. I want to find a formula for the product, integral of the product. Okay, so if you don't mind, let me just solve one more example. So let us use this and solve this integral. Okay, so how should I know that it might be the case that the integration by parts will be relevant to this problem? First of all, if you are good in integration, you see that usually the main method, which was U substitution, is not working here. This is one reason. Of course, the first reason is that this is not in my table. The second reason is that it is not U substitution. And then it is a product. So it motivates me, might be this is the trick. And if this is the trick, then it shouldn't be hard for you to understand what to do. Of course, you have the option. If I write it in that way, no one knows, is this little u or is this little u? Because there is no difference. This might be ux, vx, or the other way around. I don't see the difference. So it means that that is up to me to assign one of them to be little u, to assign one of them to be little v. Okay? But there is nothing very specific that I can talk about, but a rule of thumb is that because I need capital V, I take that one V so that its integration is easy, because I want to find a primitive function for it, you know? So this one, if I take this one, little v, then because of this capital V, I need to integrate this in order to find capital V. If I could, of course, the formula is still valid, but I think you agree with me, this is troublesome. So this is why I will not give the role of V to this one. I give the role of U to this one. And I give the role of V to this one. So, as a rule of thumb, if you want to assign one of them to be V, take that one so that you can find its primitive function more comfortably. Yes? Is that right? So, if I take this one V, I have to integrate arctangent, and I don't know how to do it. Of course, that's also another integration by parts. You can do it later. But this one is easier. So I will take this one V and this one U. And then what I do, I put it in the formula. But before putting it in the formula, I need two ingredients. I need capital V. I need the derivative of U. So it might be good if I do them here. So I need capital V. So can you tell me what is capital V? One of them is enough, because you know that there are infinitely many of them. All of them differ by an additive constant. So what is integral of x? Extremely easy. So it is x squared divided by 2. And then one more ingredient I need is u prime. So u is arctangent. So I need to find u prime. So you need to remember the derivative of arctangent, which is 1 over 1 plus x squared. And then the formula is ready for you. So using the formula, let me write it down here. U, which is this guy, multiplied by capital V. Capital V is x squared over 2. And then minus integral of u prime, which is this expression, multiplied by capital V, which is x squared over 2 dx. Is that right? So, as I told you before, this method is useful because this formula is always true, but it is not always useful. It is only useful if the new integral becomes simpler and manageable compared to the original integral. And if you have a little bit of experience, you realize that yes, it is manageable. So I will go to another line. So I would rearrange them. I prefer to write this here. So I would write it as 1 over x squared multiplied by arctangent of x. And then here you see what happens. There is a factor of 1/2 which is multiplied, so I can pull it out, and this x squared will be multiplied here. So this becomes minus integral, so minus 1/2 integral x squared divided by x squared plus 1 dx. So the integral that I have, if you don't mind, let me call it I. I want to calculate I couldn't calculate it yet, but I reduce it to a new problem. So then, if you don't mind, let me call this one J and try to calculate J. So how should I calculate J? J is equal to integral of x squared divided by x squared plus 1 dx. This is one of those problems that I skipped when I was teaching, okay? But now we can do it here. By the way, this is the topic of today's lesson. We will learn about these kinds of integrals very systematically. But this is so simple, I hope that you can tell me what to do.
U substitution?
U substitution is not good here. You know why? Because if I take this U, its derivative becomes 2x, but here x squared appears.
Can you not say that it's the numerator is U minus 1, and then you have U over, and then you have
No, but the problem is that when in U substitution, you have to calculate U prime. And when you calculate U prime, it gives you 2x. But what you see here, 2 is not important because that's a multiplicative constant, but you have x squared. For example, if this 2 was not there, I agree with you, that's a substitution.
No, you could just use substitute and then integrate with respect to U.
It doesn't work.
It doesn't work.
Okay, let us do it here. So U is x squared plus 1. Do you remember what I told you immediately after that? You have to take du. So du becomes what? 2x dx. Okay? And then what I have to do, I have to write j is equal to the integral. The denominator, I agree with you, is u. But I have to get rid of x everywhere. So now tell me what to do.
What I remember from high school is that we just find a relationship for just dx. For example, dx is
yes,
du
you are right. You find it here, no problems. So, but dx becomes equal to du.
Yeah.
Divided to 2x. 2x will survive. That's what I'm saying. This is x.
I get what you're saying,
So you will have a mix of x and u, which is not allowed.
Okay.
Yes, that's what I'm saying. If it was 1 there, then it was working.
Okay.
Yes, that's not working. Okay, and then I want to choose another letter because I used u somewhere else. So let us choose, instead of u substitution, if you want to talk about t substitution. But this is not substitution. So any other, yes?
You do the integration response again.
This is possible, but this is much simpler than that.
We split the fraction into partial fractions.
No, not yet. No, well, okay, so let me write it. If you don't have experience, you will. We'll talk about this systematically today. This is, I was thinking that you might guess. I would write x squared plus 1 minus 1. Okay? Yeah, might be, okay, so might be that's a little bit troublesome, but integration needs a lot of practice, by the way. So this is first of all legal, yes? I haven't done something wrong. I have added 1, subtracted 1, so I did nothing. But why this is useful? Can you see it now?
Split it.
Yes, I can split it now. I can say this divided by that minus the other one divided by that. So everything is correct. But I want to prove that this is not only correct, but useful. X squared plus 1 is just simply 1. And then 1 minus x squared plus 1. Okay, dx. This one is not a problem. So I can split my integral into 2 parts now. So integral of 1 dx, you don't need even to write 1, minus integral of 1 over x squared plus, if you don't mind, I don't know how many of you have this in your memory. This is a very famous function. We have it on the board, by the way.
Arcsine?
Yeah, it's arctangent. Yes, so I would write it as 1, and then the answer to this part is simply
It's
x.
minus,
This is just on the board, okay? So this is, but one of the formulas you need to remember. So it's minus arctangent. Of course, I have a constant c, but I prefer to add everything at the end. So now we go back to I. So how should I calculate I? It is done. Because I is up there, is equal to 1 over 2x squared, and then arctangent of x minus 1/2 times j. So 1/2, and j is calculated to be x minus arctangent of x. And then when it is finished, I prefer to add a constant at the very end, not case by case. I don't know, you cannot simplify it that much, but if you want to make some things a little bit beautiful, you multiply this and factor that one, so it becomes like this. But I don't think the last step is necessary. Any questions? Yes.
With so many integration methods, how do you know? Is there any some kind of trick to know which one to put U and V?
Yeah, I told you. Usually the one that you, because you know that in the formula that I have written, if you have a product, this is already an indication that is a good trick to do it here. but you don't know which one is u, which one is v. I told you, as a rule of thumb, it is better to take the one whose integration is easier to be v. So if I take this v, because I need capital V, I have to start right away with an integral. Okay? So I will take this one. But sometimes there are some deviations to this rule of thumb. You have to do a lot of practice to see. And there are very good questions in the book. And I have solved many hard problems of the course book on the video. So I put the links for you there. Okay, but one thing that I want to mention is that usually this is the Swedish way. This is when I came to Sweden, I saw this method, which is a very good one. But usually the books, I want you, if you are reading the book, I want you to get familiar with the notation in the book. The book calls this little dv, and then you have u dv. So let me write it here for you. So if you see in the book, the formula will be integral u dv. They want to make it very short, so they are just suppressing the x's as well. So u dv, and then this one multiplied by that one, as we learned before, together is called du. And then they are suppressing x's, so the formula becomes u v minus integral v du. That's also, this is the way I learned when I was doing integration by parts. It's easier to remember. So integral of u dv is uv minus the other way around, v du. But if you want to solve this problem using that, then if I go back to I again, so I would write my I, but because of the same rule of thumb that I mentioned, I write it the other way around. I would write it as r tangent x times x dx. This is the same integral. But what I do, I will call this one u, and I will call this combination dv. Then I becomes u dv. Okay? And then on the right hand side, I need u, I have it. I need v, still I don't have it. So this means that because I myself took dv to be x dx, v is nothing except this simple integral. This is the way the book is done. So it is x squared over 2. Okay, and then what happens? You see I need du. I have u. So u is r tangent of x. So this means that du is the derivative of the function, which is the same thing, but you have to multiply it by dx, as we learned in u substitution. Okay? But if you put these information back into this little formula, you will exactly get the same thing. It will not solve something easier for you. It only makes it easier to remember. Okay? But if you have a good memory, that's also good. It doesn't matter which one you put. And of course, the rest of it will be clear. So let me change my color, because the answer will be uv. This is my u. This is my v. If I multiply it, exactly becomes the same expression as you see there. Minus integral v du, the other way around. This is v, and this is du. But I don't want to continue because they're exactly identical. Yes? That's up to you how to use it. But now, any questions? So let us now go to the next topic. That is the last integration technique that you learn systematically in this course, a method of partial fractions. So, the method of partial fractions, one of them is something we did today. So this is, the topic is that you have an integral, you have a rational function in front. What do I mean by a rational function? It is a fraction whose numerator and denominator are both equal to a polynomial. Yes? So let me call the polynomial in the numerator p of x. Let me call the denominator polynomial to be q of x. Okay, so we consider, so do you know a polynomial? Yes, for example, x squared plus 1 is a polynomial. A polynomial is an expression without fraction powers or without negative powers. It's just polynomials. Okay, and then you know what is the meaning of the degree of a polynomial. The highest exponent in a polynomial is called its degree. Okay, if you want to understand, so this is today's lesson. If you want to do it, we have to know about the degrees. We consider two different cases. One case is the case that the degree of the numerator is strictly smaller than the degree of the denominator. And another case is the case that the degree of the numerator is either equal to this degree or greater. For example, this is one of those cases that we solved today. The polynomial x squared divided by another polynomial, and the degrees are equal. So this will be the second option. Okay, but in order to understand that, we split this into different problems. You have to somehow memorize some formulas. Okay, so case number one, I will consider the case that degree of p of x is less than degree of q of x. This is what I want. Okay, but then I will consider two special cases. One special case is that degree of qx is 1. Okay, so if the degree of qx is 1, what can you write for qx in general? Qx is a polynomial of degree 1. So in general, it is ax plus b. Yes? And of course, because I am now myself assume that degree of p should be, I am considering those cases that the degree of p is smaller than the degree of q. If the degree of q is 1, so there is only one option for degree of q. What is the, degree of p? So degree of p should be what? 0. So it means it is a constant number. It's a constant number. In this case, method of substitution works very nicely. So let us do that. So what happens? And if you don't mind, let me call my integral in this topic I all the time. Okay? So what happens? I becomes equal to the integral. The numerator is a constant. The denominator is ax plus b. And then I have dx here. This is the integral I want to solve. This is U substitution, but I think if you remember the formula, you don't need to waste your time. You can just use the formula. But if I want to use the formula, so I will introduce U to be, if I want to derive the formula, then I take du. So du becomes the derivative, which is a times dx. And then I rewrite this in terms of u. So this becomes integral. C is just a constant. Instead of ax plus b, I put u. And instead of dx, I have to put 1 over a du. Do you agree or not? Understandable? Okay, but then c and a are constant. I pull them out. So this becomes integral of 1 over u du. But this is a very famous integral. That's ln. So it becomes c over a, ln of absolute value of u, and then plus a constant. But then whenever you use substitution, you have to switch back to the original variable. So it becomes c over a, ln of absolute value of ax plus b plus c. Okay. So essentially, this is nothing. This is very a special case of this general case that we are studying, but this is just method of substitution. Okay, but now consider another scenario. And another scenario is that the degree of qx is 2. If the degree of qx is 2, what happens?
Another special case.
Yes, that's another special case. Then we just talk about it generally. So another special case is that I have degree of qx 2. So what options I have now for degree of p of x? Because still I am under the same assumption. I am only considering this case first. Yes. So if degree of q of x is 2, so what options I have for degree of p?
Constant variable.
Constant or a first degree variable. Okay. So I will consider the constant case and the one degree. For example, I can say that x is a constant. So let me write. This means that the degree, if you don't mind, by the assumption a, degree of p of x is either 0 or 1. So in these cases, 4 integrals you have to remember or you have to be able to derive. So one formula is like this. So I would write integral. In the numerator, I put degree 0. And if you see that here, I could have written 1. In the book, by the way, it is written 1, because if there is a number not 1, I can pull it out. So let us consider that the numerator is 1. And the denominator is of this form, x squared plus a squared dx. This is one of these cases, yes? The denominator is degree 2, the numerator is degree 0. Of course, I could choose any other number, but that is a minor problem. But this is already you know. Do you know the answer? Arctangent. So it is 1 over a arctangent of x over a. And then you have plus your constant. Another scenario is I have x squared minus a squared. I want to do it separately. This is another one that we need to learn. This is a little bit tricky. I just want you to learn how to do it. So in order to do this integral, I would write it as x squared minus a squared. I would write it as 1 over x minus a minus 1 over x plus a. Don't worry about that. I will tell you why you should understand this can be done. But here, I just want you to see what I have written is true. Do you agree? Because if I take the common denominator, they will be multiplied and I get this back. Okay, so I have to adjust it. This is not completely correct. And then what happens, this go here, minus this go here. So this becomes x plus a minus x minus a. Okay, what do I get back? When I open it up, x's are gone. A plus a becomes 2a. But the numerator was 1. So I am a little bit in trouble. But I can immediately solve that trouble. Tell me how. So you see, this equality is not 100% correct yet. Because if I collect it, the denominators will be exactly this. I do not have any problems, but this will go here minus this will go there as the common denominator. When I open it up, it becomes 2a, but I have 1 here. So in order to make this correct, I have to do some adjustments. What that adjustment is?
Multiply the right-hand side by 1 over 2a.
2a, very good. So that's exactly what I want to do. I will multiply it by 1 over 2a. Yes? So what I am telling you, you will learn why you can do these things in a systematic way. But for me, for the time being, just accept it from me. What I have done is correct. But now, if I want to calculate this integral, instead of calculating this integral, I can calculate 2 different integrals and then subtract them. So if I do that, what happens? So this means that this becomes equal to 1 over 2a is a constant, and this becomes integral of 1 over x minus a dx. And then I have minus integral 1 over x plus a dx. What happens now? Both of them are of this type. Now, you see, so we are going back. You see, this one is very comparable to this one. If you compare these two, compare this one with that one. C is 1, yes. A is 1, and B is minus A, yes. And the same story here. C is 1, A is 1, and B is plus A. So I can use that formula 2 times. 1 for this one, 1 for that one. So what happens? This becomes 1 over 2a, and then this becomes ln of absolute value of x minus a minus ln of, I'm using that formula, x plus a. And then at the end, I have a constant c. Are you following or not? Yes? But you know a formula for ln. ln of a number minus ln of another number, I can write it as ln of a fraction. So this is why this formula you need to know. So let me write it here for you. So the integral 1 over x squared minus a squared dx is nothing except 1 over 2a ln of absolute value of the division. So you can consider them as small practices for integration. But these are the formulas that you need if you want to solve harder problems of that type. Okay? And we are going systematically. So I am considering that the degree of the denominator is more. So I already did this special case. I am considering these special cases as well. So these are the cases that the degree of the numerator is 0. But there's two other cases that the degree of the numerator is 1. So one of them is integral x divided by x squared plus a squared dx. And the other one, I just want to write the answer, but let me do this one here. How can I do this one?
Arc 10,
This is U substitute.
arc 10 times x.
No, be careful. I told you that the product does not work like that. Yes, but this is U substitution now. How? I introduce U to be x squared plus a squared, and I take du, so du becomes 2x dx. But do you see what I need? I need this combination, x dx. So x dx becomes what?
du.
What is the strategy? The strategy is to throw the old variable out in favor of the new variable everywhere. So this integral becomes integral. Instead of this combination, I put 1 over 2 du, and in the denominator I have x squared plus a squared. Sorry, u. But then this is extremely familiar integral, yes? So it becomes du over u. But what is the answer? It's just ln of absolute value of u plus a constant c. But what is u now? I have to switch back. Yes? But do I need absolute value here? I have to put it, but I can remove it now because I am on the safe side. X squared and a squared are just non-negative numbers. When I add them, it becomes positive. So this becomes 1 over 2 ln of x squared plus a squared and then plus c. So this is the third formula. So let me put them in a box for you. So here, this one. We also have this one. We also learned now about this one. And we also learned, let me write it immediately. X squared plus a squared dx is 1 over 2 ln of x squared plus a squared plus c. So that is the third one. And the fourth one, I hope that you can tell me immediately. The fourth one is this one. I just want to write the answer because the derivation is extremely similar to the previous case. Can you guess this one? If instead of having x squared plus a squared, I have x squared minus a squared. So what will be the answer? Do you see that which method works here as well? Substitution. Yes? So if I substitute x squared minus a squared to be u, then the numerator exactly as before becomes 1/2 du, and this becomes u. But when I replace u, it becomes x squared minus a squared. So this becomes 1 over 2 ln of absolute value of x squared minus a squared plus a constant. Can I drop absolute value in this case? No, because there is no guarantee which one is bigger. So in this case, I have to keep the absolute value. In the other cases, I don't have to. Any questions so far? So are you following what we are doing? We are going to talk about that integral in general, polynomial divided by polynomial. From the very beginning, I divided the problem into 2 separate groups. I am considering the first one. The first one is the case that the degree of the numerator is less than the degree of the denominator. And for this, I am considering 2 special cases. The degree of qx is 1, so there will be degree of p 0, or the degree is 2, then I will have degree of p 0 or 1. Yes?
Sorry, could you go over again about how you split the fraction?
No, here I didn't tell you in a systematic way. I wrote the formula for you, and I asked you to, do you believe in it or not? By doing some calculations, we started believing that this is true. And I use this to find my formula. But a little bit later, I will tell you how to think about these kinds of splitting fractions, which is called the method of partial fractions, in a systematic way. Yes? But for the time being, you have to make sure that what I have written is true. If that is okay with you, that is the only thing we need. Okay, any questions? Yes? Okay. So let us solve two examples here. So for example, I call this I integral. I have it x minus 1, x squared plus 4. Is that like right? Yes. We want to do this. So what is I? Okay, so let us review quickly. So do you see that this question is relevant to this topic? Why? Because it is the integrand is a fraction whose numerator and denominator are both polynomials. And the degree of the numerator is 1, the degree of the denominator is 2, the degree of the numerator is strictly less than the degree of the denominator. So in principle, we should be able to solve it. Okay? Okay, so how should I continue now? So you need to learn this as well. Yes.
Split it in two cases.
Split in two cases. If you are so you have a good sharp memory that you know about these, then it is not hard to see. Splitting it in two fractions, it will solve the problem. So what I will do here, so this becomes integral. So I becomes integral. I write this divided by that, and then minus this divided by that. Probably this is the simplest one. And then I know that I can split my integral into two integrals, x over, and instead of 4, if you don't mind, let me write 2 squared, because I want to mimic the formulas here. And then I have dx, and then I have minus integral 1 over x squared plus 2 to power 2 dx. And I hope that you see that we are done. Yes? Which one is this one? This one is here. A is 2. And the other one is, which one? Is this one. Yes? So let us just put them in place. So this becomes 1 over 2 ln of x squared plus 4, yes, and then minus 1 over a arctangent of x over a plus a constant. Understandable? So let us do another example. This is a little bit more tricky, but you need to also learn this method. So I want to deviate a little bit from what I said. So I have x over x squared plus x plus 1. This is a little bit harder. But still, I hope that you agree with me, this is still in the same category. Yes? Because the integrand is a fraction, the numerator is degree 1 polynomial, the denominator is degree 2 polynomial. So still it is in the same category. But apparently none of these formulas is helping. Because in all the formulas that I showed for you, I have only 2 terms in the denominator. But here I have x squared plus another extra x plus 1. If this x was not there, that was okay. But unfortunately it is there. So how can I get rid of it? This is a very high school method. It is called completing the square method. Yes, so you should hopefully know how to complete the square. Yes, I will not repeat it. It is written in the book as well. The formula is there. So how can I complete the square? Do you remember? So let me write, complete the square. So integrations mostly relies on your memory. So you have to know the techniques. So complete the square. So what do I mean? In the denominator. In the denominator. Yes. So x squared plus x plus 1. So I can write it as between these two. I can write x squared plus x. Let me also briefly tell you what to do. And I copy and paste this one. And I ask myself what number I should put here so that I can write it as a completed square. As a square of a binomial.
1/4.
1/4. Yes. If I put 1, and then what is the rule of thumb? Whatever number is here divided by 2, the number here is 1. When you divide it by 2 is 1/2. When you square it is 1/4. So if you couldn't guess, divide the middle number by 2, square it. That is your magic number. But you are not allowed to put 1 over 4 there unless you compensate for that change by subtracting it. Because I'm not allowed to change the problem, yes? So then these 3 become what? X plus 1/2 to the power of 2. And 1 minus 1 over 4 becomes 3 over 4. And if you don't mind, let me call this integral j this time. So I rewrite j and I ask your opinion. How to continue? Okay, you can think a little bit, so I'm a little bit bored. So let me see if I pause this. Did you come up with a solution? So I wrote it here for you.
Use substitution and make u equal x.
Yes, so that is the trick. If you have all 3 terms, the idea is to do complete square and then use u substitution. What should I take as u? Can you tell me?
X plus half.
X plus half, yes? So I will take then, I would say u is x plus 1/2. Then what happens? Du becomes the derivative, which is 1 multiplied by dx. And then I rewrite this integral in the form, in terms of u. So, therefore j becomes what? Okay, I have to rewrite everything in terms of u. Be careful about that point. So x plus 1/2, I took it as u, so it becomes u squared. Okay, and then I have 3 over 4, that's just the number. But dx, I don't have any problems. I write it as du, but still I have a problem with the x itself.
U minus half.
Yes, because I have to get rid of this x in the favor of u. So it means that I go back here and find x here. It becomes u minus 1/2. So I put it here. So it becomes u minus 1/2. Is that right? Okay, but now can you see the problem is solved? Because now again I can split. So how can I write it? I can write it as integral u over u squared. If you don't mind, let me write this in the form of a square. Yes? Because the formulas I need are x squared plus a squared. So intentionally I wrote it like this. So this is not a. What is a? A is the square root of 3 over 2. And then I have du. And then this minus goes out. Then I will have du divided by u squared plus the square root of 3 over 2 squared. Is that right? But this is doable. Which formula? Do you see any sticker around here? Ah, yes. So, do you see which formula is suitable for this one? Of these ones in the box? For this one? Yeah, this one. And what is playing the role of a? Square root of 3. So you use this formula. Instead of x, you have u. Instead of a, you have this one. But a squared is still the same number as 3 over 4. And this one, which is useful? This one, yes? And then if you don't mind, for saving time, you can do it yourself. So what you do, you use those 2 formulas, write these in terms of u, but there is one more step. What is that? Switch back to the original x. So if you want, I can do the first one. So let me do this one. So it becomes 1 over 2 ln of u squared plus a squared. Yes? Minus, I keep this one for you. But this is not finished. I have to replace u with what I had before. Yes? So this becomes 1 over 2 ln of x plus 1/2 squared plus 3 over 4. You do something similar for the second case. But then if you want, you can open it up. It goes back to x squared plus x plus 1. It is simpler. So it becomes 1/2 ln of x squared plus x plus 1 minus and then plus s. Yes? Yeah, understandable or not? Yes.
Can we not just use the formula we used on the top?
This one?
No, the bottom one. Integral of x over x squared plus a squared.
This one?
Yeah.
I use that. I use that formula here.
No, but before we split it in and you
Here,
before
I don't
you
see
start.
any. I don't see a way for doing that.
Because when we had split it,
No, because are you talking about this formula? Am I right? Okay, so if you compare this one with this one, this structure in the denominator is exactly this structure. I agree with you, but the structure of the numerator is just one simple x. If minus half was not there, it was right. But because of minus a half, I have to split.
I was talking before we use U substitution.
So here you mean?
Yes, there.
So how should I do that then?
We have the j integral,
Yes.
and instead of x squared, we just say x squared is just x plus 1 by 2 the whole square.
No, that doesn't work. Because no. That's a good question you ask. This a is a constant. So you can say that I can split it like I understand what you say now. Something like this. Are you talking about this?
No. I meant if we have the denominator x plus 1 by 2 the whole square
Yeah.
In the j integral.
Yeah.
So we say that the denominator x plus 1 by 2 is nothing but x in the formula.
No, that's what I'm saying. In that case, you will miss this minus a half. Minus a half brings you another new integral. So whenever you want to think in those terms, in integration, okay, that means substitution. And substitution, you cannot say that, okay, x plus 1/2 is similar to x. So let us work with it as if x plus 1/2 is x. No, it will have some effect. The effect will come here. If you do like that, you don't see this minus a half. And then you will not see this second integral. But the correct answer is with that second integral. Is that understandable? Yeah. Okay. Any questions? Okay, if you really need a break, might be that's a good time because then I want to talk about the most general case now. But 5 minutes, okay? Thank you.